Bismillahirrahmanirrahim. This is electric circuits course of second semester students, and this is a textbook. I'm Dr. Khalid Hassan in the Department of Electrical Engineering. We are discussing chapter 8 on steady state response. Only section 8.1 or 2 are included in this course. This is part 2 of a lecture on chapter number 8, and this is the last lecture of this course as well. We have seen from the previous lecture that resistors in phasor representation, the voltage current relationship of phases of resistors in phases is VR equal to RIR, and the inductor VL J omega L IL, this is inductive reactance, and capacitance VC, this is 1 over J omega C or minus J over omega C multiplied by IC, this is capacitive reactance. And in general, we will call it V equal to Zi. So this V equal to Zi, in this expression, Z is called the impedance. Please change this. This is a spelling mistake. This is a typo. Impedance. Impedance of the element, of the circuit element. So impedance of the resistance is R, impedance of inductance is J omega L, impedance of capacitance is minus J over omega C. And passive sign convention we follow is the same as that we have discussed in previous chapters. Resistance, current flowing from left to right, and this is the polarity of the voltage across resistance. Inductance, this is the phasor current and the phasor voltage, and inductance behaves like an element with J omega L. So the capacitance C is replaced with the 1 over J omega C. This is simple. Whenever we see a circuit with resistance, inductance, and capacitance, we will replace resistance by R and inductance by J omega L and capacitance 1 over J omega C. That's it. So we should know the inductance and the frequency, capacitance and the frequency. We don't need to know the frequency in order to determine the resistance, because the behavior of the resistance is same at all frequencies from omega equal to 0 to infinity. We'll see it in the following slide. This is from the following slide, and this Z, it may be a resistance, maybe inductance, maybe a capacitance. Passive sign convention will be followed. Now the impedance relates phasor voltage to phasor current. This impedance Z, please follow the cursor, Z, it relates the voltage across an element to the current through that element. It's a complex quantity with the units of ohms. Although the impedance can be complex, in case of resistance, it is only real. In case of inductance, it is complex, only the imaginary part. In case of capacitance, only the imaginary part, which is complex. Now, we may have a combination of resistance and inductance and capacitance in a circuit, and there will be the net or the equivalent effect of all the components or the circuit elements will be the net impedance or equivalent impedance. Phasors represent sinusoidal signals, while impedance characterizes circuit elements in the sinusoidal steady state. We'll see in the next slides, in the following slides, that this impedance, it is used to characterize circuit elements. Impedance used to characterize means used to show its behavior with respect to frequency. So this capacitor ZC is inversely proportional to the capacitance, the frequency, and ZL is directly proportional to the frequency. The passive sign convention is used to assign the reference marks to the voltage and the direction of the current. Effects of frequency on impedance, as I have said before, there is no effect of frequency on the resistance. However, j omega L, inductor ZL is directly proportional to the frequency, and capacitance ZC is inversely proportional to the frequency. Magnitude, it has magnitude R and angle 0 with the resistance. What is the magnitude? Omega L, and the angle due to J, the angle is plus 90 degree, and this, the magnitude is 1 over omega C, and due to minus J, the angle is minus 90 degree. The magnitude of resistance and the magnitude of the impedance of the resistance and the inductance and the capacitance. And now we show this graph shows the dependence of ZR, ZL, ZC with the frequency. This is the horizontal axis, this is the frequency axis. We start from 0 to infinity. At 0, when the frequency is 0, we call it a DC signal, frequency 0, DC signal. And resistance, its value remains same at all frequencies. And in case of inductance, omega L, it increases linearly with the frequency. So when the frequency is 0 for DC signals, it is 0, and when the frequency is very high, when the frequency is approaching infinity, the magnitude of ZL will also approach infinity. ZC, it's a different. When omega is 0, its impedance is infinite. So infinite impedance means it behaves like an open circuit. You will see quickly. And as frequency increases, because it appears in the denominator, omega appears in the denominator, inversely proportional. So this curve shows the magnitude of the capacitive impedance. Now, again, this table will help you to understand the behavior of resistance when frequency approaches 0, when frequency approaches infinity. Resistance behavior of the resistance remains same. But in case of a capacitance, if frequency approaches 0, capacitor behaves like an open circuit under DC conditions, and when the frequency approaches infinity, it behaves like a short circuit. So impedance capacitive, capacitor behaves like a short circuit. As the magnitude of Z, C, it becomes 0. So the inductor is, the behavior of inductor is dual to the capacitor. Inductor behaves like a short circuit due to 0 ZL if the frequency approaches 0 or at frequency 0. This is the magnitude of ZL. So 0 means a short circuit, and as frequency approaches infinity, magnitude of ZL also approaches infinity. So infinity means it behaves like an open circuit. Now, this is ZC and this is ZL. When the magnitude of ZC and ZL, they become exactly same. This is the intersection over here, and it occurs as a frequency, and this frequency, it has a significant role in circuits and in systems, and this frequency, where the magnitude of the impedance of inductor equals to that of the capacitor, is called resonant frequency, and it is an important property of circuits in sinusoidal steady state that we can use to our advantage. In here, this is the resonant frequency, and at the resonant frequency, the magnitude ZL equal to the magnitude of ZC. Magnitude of ZL is omega L, magnitude of ZC is 1 over omega C, and due to this equivalence, the frequency can be, we can determine this frequency as 1 over, knowing L and C, as 1 over square root L times C. In this example, current in phases is shown 4 with angle 0. So if I interpret it in time domain, it will be 4 cosine omega t and we must know omega. What is omega? So this is a circuit, and in this circuit, the source, the excitation, the VT, the current in it, the current flowing through it. And look at the cursor, the current IT. This current is 4 cosine 5000t. In phasor representation, this current is represented as 4 and the phase angle is 0, so it is I. Now we see how in phasor analysis how we deal this circuit. So in phasor analysis, what is ZR? ZR is equal to R10 plus J0, ZC 1 over J omega C, it is minus J20. And therefore VR, the current in phasor current multiplied by 10, this is the voltage across the resistance. The voltage across the capacitance is ZC multiplied by R in phasor, ZC. So this is ZC we have seen, and this is the current 4 plus J0. This is the current 4 plus J0. It is 4 cosine 5000t with angle, phase angle 0. So this is the phasor representation of the capacitor voltage and the resistance voltage. The net voltage over here is VR plus VC. So we can add phasors. So VR plus VC is shown over here. So it is 40 minus J80. 40 minus J80, the magnitude is square root of 40 square plus 80 square. This is the magnitude, and the angle tan inverse of minus 80 divided by 40. This is the angle. So this is the phasor representation of this voltage. Phasor representation of this voltage. As I said before, in time domain, the capacitor, it is 10 microfarad, and in frequency domain, in the phasor form, this capacitance will be represented as minus J divided by omega C. Omega and C are given. For given omega C, it is minus J20. So this is the only thing we need to do in the phasor circuit analysis. We consider capacitor as minus J over omega C and inductance as J omega L. Resistance remains same. Now the voltage over this voltage, we convert this voltage which is represented in, we have found the voltage in phasor form. How we can represent it in a time domain? See, the magnitude will be shown over here as the coefficient of cosine, and 5000t, 5000 is omega. Note that information of omega is missing, phasor does not represent the frequency. There is no indication of frequency over here. So it is 89.4 cosine. Remember, it is the cosine function. It is 5000t minus 60. So it consists of only the magnitude and the angle. So this is the magnitude and the angle. Again, it is the same circuit. I have just reproduced it, but here I want to show the graphical representation of the voltage across resistance, voltage across capacitance, current, and the impedances. So this current, we know that the current over here, the phasor current is 4 angle 0. So this is 4. The line, this is 4 with angle 0, means it is 4 plus J0. So it is on the real axis, and this is the imaginary axis. And the VC is I haven't shown VC over here. So VC is, sorry for that. VC is minus J80, minus J80. So minus J80 will be a line over here. So I will draw it for you. So minus J80. So it will be minus J80. So it will be like this over here, minus J80. And VR is 40 with angle 0. So IR and VR are same. So this is VR. So VR plus VC. So if we add these two, VR and VC, we have the sum of VR and VC in phasors form. We can represent the impedances ZR and ZC in the same manner, and we can find the Z equivalent. It's a complex quantity. Now, its representation in a time domain is 89.4, here 89.4 cosine 5000t, because we know from the source, and the angle minus 60. This is the angle. Now we show it in over here in the waveform. So this is the current. So this current is IT. The current IT. There is no phase angle, so it starts from the peak. It is perfect cosine function, and the voltage over here, its peak value is 89.4, and its phase angle is minus 60.4. So if we assume if we assume zero phase angle, if this is zero, it is only 89.4 cosine 5000t. It should start from here. It should start from here. So due to the phase angle over here minus 60, so the origin has been shifted towards the negative side by an amount minus 63.4, and this is our phi. So this is the time domain representation. This is the time domain representation of current and the voltage. Note that the peak value of the current is 4, while the peak value of the voltage is 89. This is, mind that, this is peak value 89 and this is 4. Phasor circuit analysis continued. You have seen the circuit analysis technique discussed in chapter number 7, and the response. How we find the response of this circuit. Response over here means the voltage across the capacitor. How we find the voltage across the capacitor. Sorry, if you remember, we write differential equation, and it is first order circuit. We write differential equation and we find the solution of the differential equation to have Vt in time domain. I have discussed this in my lecture on chapter number 7. So we found that the voltage across the capacitor is V0 minus VA over 1 plus omega RTC square, with an exponential function over here, E minus T over tau. Tau means RTC plus VA over square root, this the same quantity, and cosine omega T plus theta. See my previous lecture on chapter number 7. You may be able to recall this, that this is the response, but this is the complete response. Note that in here we have due to this exponentially decaying term, this term will be exponentially decaying with respect to time. If I draw it, this term will be exponentially decaying due to minus T over RC. So this term will be like that. So this is exponentially decaying term. As time t approaches infinity, this term disappears. As time t approaches infinity, this disappears, and this is then the steady state response. Steady state response means when the circuit has been settled in a state as t approaches infinity. So this is the steady state response. Now I will delete it for clarity. And then the steady state response as time t approaches in only the second term. This is the steady state response. And for given values of RT means Thevenin equivalent of Thevenin equivalent resistance seen by the inductor. So we have discussed it before. The Thevenin equivalent in the Thevenin equivalent circuit seen by this inductor, the Thevenin equivalent resistance is 4K in parallel with 4K. You know, we short circuit the voltage source, so it is 2K, and RT, the RTC is the time constant, and theta is tan inverse of, we have discussed it in the previous lecture. And what is the Thevenin equivalent voltage seen by this? So in the Thevenin equivalent voltage we will have, because we have 4K and 4K, so it's a voltage divider, so half of the voltage over here, so it will be 10 cosine. So if we substitute V is seen by Thevenin voltage seen by this 1 microfarad, so and it is in I think it is in VA, the peak value is 10 cosine 1000. So it's from chapter number 7. If we substitute these values in this expression, we have 4.47 cosine 1000 t minus 63.43 degree. Please verify it. There may be some typo in it, but I have checked it, but there may be some typo in it. So we have to write the differential equation, find the solution, then see what is the steady state response, then substitute values in order to find the response in time domain. Now this is the circuit. So how we analyze this circuit? With the help of phasors. So with the help of phasors, we represent everything in phasors. So the input voltage 20 with angle 0 volts, and resistance remains same, 4K remains same. However, the capacitor will be minus J over omega C. So if you find minus J over omega C. Now as we want to find the voltage, capacitor voltage, we can use mesh analysis, mesh 1, mesh 2, or we can use node analysis. There are 3 nodes: ground node, this is ground 1, node 1, and this is node 2. We know the voltage at this node, it is 20 with angle 0, and we have to write only one equation at this node, and this current, writing node equation, this current will be V minus 20 divided by 4000. This current V minus 0 divided by 4000, and this current is V minus 0 divided by minus J. This is important, minus J minus J 1000. We proceed further, and we find that V is equal to 20 divided by 2 plus J4, and in a phasor form we express it as 4.47 with angle minus 63.43. Note that now if we want to convert this into the time domain response, it will be 4.47 cosine omega t minus 63.4, which was the same as that we have achieved in the time domain solution. Note that in the circuit analysis in time domain directly, we have complete response. We have to identify the steady state response to reach the final conclusion, to find the required response. In phasor domain, we just represent capacitor as minus J over omega C, resistance remains same. If we have inductor, it is J omega L. We write either loop equation or node equation. We find the response in phasor domain or in the phasor form, and then we convert this into the time domain. I have discussed in earlier slides of this lecture. Now this is another circuit, and this is a second order circuit. Those second order circuits are not included in this course, but there is no harm to see how we analyze this. So at present, it is the capacitance is directly represented in phasor form. The inductance is directly represented in phasor form. J200, we don't know inductance, we don't know the frequency, but we know J200 is the phasor representation of an inductor and the capacitor as well. So in here we have node 1, node 2, node 3 are A, B, C, and this is the ground node, and we write equation for this node VA minus 0 divided by minus J, and then this current is VA minus VB divided by J200, and this current VA minus VC divided by 50. Similarly, we write equation at node B, and writing equation at node B, we have two equations and two unknowns, VA and VB. You may say that VC appears to be an unknown voltage, but VC with respect to ground, it is directly given, it is 75 volts. Angle 0 means it is just 75 volt, or if you insist, it will be 75 for J 75 plus J0. So VC is known. Only two voltages are left to be determined, VA and VB. So we have two equations and we can find VA and VB. You should do it by yourself. So this is VA and VB in rectangular form, and over here in phasor form, over here we in a polar form it is 73.58. From where 73 came? It is the square root of 70.4 square plus 21.4 square, and the angle is tan inverse of minus 21.4 divided by 70. This is the angle VB, this is the angle VC, 75 angle 0, we already know. And then we can convert it into time domain representation. 73.58 cosine omega t minus 16.9 degree, and similarly VB and VC. So you see how quickly we have found the response in phasor. Due to the phasor analysis, we have find VA, VB, VC, and then at the end we can convert it into the time domain representation. Note that this is the steady state response. The transient response is not included in it. Analysis in the phasor domain from a previous slide, number 11, we have found that we end up over here. This is the circuit response we have discussed before in phasor form, 4.43 minus 63.43, and in the same circuit we found that its response in time domain is 4.47 cosine this. And now a quick comparison of analysis in time domain and analysis in phasor domain. In if we proceed in time domain, we have a circuit in the sinusoidal steady state, and we write differential equations. We find the force response of the differential equation, and then we find the sinusoidal response and the waveforms. In phasor form, we have the circuit. Knowing the frequency and knowing the capacitance and resistance and inductance in the circuit, we represent the circuit in phasor domain. Inductor as j omega L, capacitor as 1 over j omega C, and resistance as such R. Then there is no d by dt or integration in it. So we directly write loop equations or node equations, which are simple algebraic equations. And we then solve these equations, and then in order to see the response, and then the phasor response can at the end may be converted to the time domain response, as we have seen in previous slides. So this is the quick comparison of analysis in time domain and analysis in phasor domain. Again, when we analyze the circuit in phasor domain, we find the steady state response. This is end of part 2 of my lecture on sinusoidal steady state response. Note that only first two. So it is first two. Only first two sections are included. So this is the typo. I wanted to include first three, but due to the length of the course and shortage of the time, I have limited the course to section 8.1 and 2, and this is the last lecture of the course electric circuits. Thank you very much.